All right. Where we finished off last time is we were talking about supernovas. So we want to finish that up right now. And let's do a quick review. We're talking about what we call type 2, or also called core collapse supernova. Now remember, this only occurs when you have a very high mass star. High mass star means significantly bigger than the sun, at least 20 times the mass of the sun or greater. Okay? That's the only time you can actually have a supernova. You will not have a supernova with a solar type star. Our sun will never blow up. It's only on very high mass stars, which are very rare. These high mass stars are very rare. They live for a very short time and then they die. But we've got to remember that what's going on in the core is what creates the supernova explosion. And by the time it gets to the point where it's about to blow up, the core has become an iron core. Okay? And then we have all these layers around the core. You remember the layers around the core we have. In the outermost layer we have hydrogen to helium, then helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and then one more in here, silicon to iron. I know you probably can't read that from there, but you should have all that in your notes too. And remember, the outer layers of the star have been continuing to grow until the star is becoming what we consider a red supergiant star. When it reaches this point, and remember, every layer, every time it changes elements it's fusing in the core, this happens in a shorter and shorter and shorter time scale. So that the first ones last for 1,000,000 years, and by the time you're down to the last one, you're talking days or hours. Everything happens quickly. And once you get to iron, we hit the magic point where iron cannot support it because of the curve of binding energy. It should be in your notes too. It looks like this, where the peak value is iron, right here. This is the amount of energy over here. And on this side we fuse elements, we get energy. This side we use fission. Okay? So fusion over here, fission over here. Remember, this is atomic number down here. So the uranium at 92 is the largest element. Down here is hydrogen at 1, the smallest element. That's naturally occurring elements. That's why you split big elements to get energy. You fuse small elements to get energy. But once you get to iron, there's no way to get energy out of it. The whole core collapses inward. The collapse changes the temperature here to trillions of degrees, destroying the iron atoms with these massive gamma rays. So much crushing of there that it actually crushes the electrons into the nucleus of the atom. The electrons and the protons combine, and you create a leftover blob of neutrons. That blob of neutrons is on the order of about 10 kilometers across. 10 to 12 kilometers across. It's just 7 or 8 miles, up to like 10 miles. That's it. So you have the whole thing, which is way more massive than our sun, but it's crushed down into something the size of Greenville. Very tiny. All right, that leftover remnant then becomes so solid that the rest of the material, free falling in here, because there's nothing supporting it anymore, hits this and bounces. It hits and it bounces. There's a massive release of energy as the gas goes flying back out. Violent things called neutrinos come flying out that help accelerate everything. Massive amounts of cosmic rays, gamma rays, all kinds of bad stuff happens when this occurs, when that explosion occurs. Okay? We will talk later about this remnant, because the remnant is usually a neutron star, but it's also possible it could even become a black hole, and that's how you create black holes. All right, when that occurs, that star, for a brief period of time, gets very bright. You see, there's no star there. These are all stars. They're just so faint you can't see them individually. But that star there almost puts out as much light as the rest of the galaxy for a short period of time. It only lasts for a few months, and then it starts to fade away. And this is how we see most of them, is in different galaxies. This one we know, this is the Crab Nebula. This was a star that blew up in July of 1054. So about 1,000 years ago. And when it blew up, it left a remnant. That remnant in there is a neutron star, a specific kind of neutron star called a pulsar, and we can see that pulsar today. We see the pulses coming from it in radio waves. Even in visible light, you can see it spinning. And this gas cloud is still expanding outward into space. Now we have more remnants of these ones. We talked about last time how the Native Americans, or not really Native Americans, before the Native Americans, what we call the Anasazi, about 1000 AD, saw this and painted this painting. This is in New Mexico, northern New Mexico. They painted this depiction of the crescent moon and a star right next to it. When the Crab Nebula went off in 1054 AD, it would have looked just like this. It was in the constellation of Taurus, and the moon passes right through the constellation of Taurus. This would have occurred. It would have been spectacular. You could have seen this star even in the daytime. So it would have lasted for quite a while.